Welcome to the Calculus, a collection of micro lectures, video lessons, and sample exercises. Let's illustrate the sum and difference rule for antidifferentiation. This rule will now help us find the antiderivative of a polynomial function which is no longer a monomial. So we have binomial, multinomial, and even trinomial forms. Of course, we already know the power rule and the constant multiple rules for both of them, which works for monomial terms. Of course, we're also going to use them here, but we are going to talk about the illustration for sum and difference rule. Now, let's say we have here a function f of x. We know that its capital F of x is antiderivative if it satisfies the following situation, that the derivative of your f of x, the capital letter 1, with respect to x would return to our f of x here. And if that is true, then the capital letter f of x is an antiderivative of your f of x. Now, since we're talking about sum and difference rule here, let's introduce another function. And let's say this is the same situation, that the capital letter g of x is its antiderivative if, again, it satisfies this situation here, that the derivative of your capital G of x with respect to x would return to our g of x here. And let's say we have here h of x, again, capital H of x here, which would satisfy, again, this situation here, okay? And say that your h of x is actually a combination of your f of x and g of x. Let's use plus minus because this would work for both sum and difference of those two different functions. Now, with all of this already introduced, let's now have here the sum and difference rule. This tells us that if we are going to take here, okay, a integral, okay, of a certain function, let's say h of x with respect to x, but given that h of x is a combination of the other two functions, so you have here the sum and difference, or rather of difference of f of x and g of x dx. This tells us, this rule rather tells us that we can just separate the two functions with respect to dx. And when we separate, we use the operation separating them, whether plus or minus. So this is the sum and difference rule. If we have here a combination of two functions, you can separate them, distribute the integral sign, and your notation for dx, or the integral with respect to x. Of course, again, we're going to show the proof of this. Let us show that from this one here, we could actually reach this portion or even this portion here. And if that is true, then your rule is now acceptable. Now, take note that in our given situation here, the integral of f of x is already identified as capital F of x, right? This would mean this is actually f of x plus minus the integral now of g of x is this one here, the antiderivative g of x. So we are going to show here the proof that the derivative of that sum, okay? So we have here f of x plus minus g of x, both antiderivatives with respect to x, should return into, again, either this form or this form here. Okay, now take note, in our proof here, we are using derivative. And we already have rules for derivative as well. We also have the sum and difference rule for derivative or differentiation, which allows us to separate them, the two functions, on the same notation, the derivative with respect to x. Okay, so this is on the rule of derivatives. We're using that to show the what do you call this one, the truth value of our sum and difference rule. And of course, once we reach here, okay, once we reach here and here, we can go back to the situation earlier that these were all true because this satisfies these functions here. So the derivative of f of x with respect to x would be your small letter f of x, okay? F of x plus minus, you will have here the derivative of your g of x here with respect to x is your small letter function g of x, okay? G of x. Now take note, what is this equivalent to? This is equivalent to this entire expression here, which is originally h of x, as we have identified as a combination of both functions. Since we have arrived into this form, that from this one here, using all those relationships we had earlier, when applied with derivative, would return to the sum and difference of the two functions. And of course, if we're going to have them under the integral, would return to this one here. This shows that our sum and difference rule is already acceptable and true. Okay, this is the proof for that. Before we end this and proceed to another video explaining with some examples, let us not forget that this rule would extend not just for two functions here, it would extend for more than or even infinitely many. Let's say we have here the integral of, let's say here, f sub 1 of x plus minus f sub 2 of x plus minus f sub 3 of x, and you have here until so on and so forth. Okay, so let's just have ellipses in that manner. Again, with respect to x, we could of course break them into separate forms. You have your f sub 1 of x dx plus minus, whichever would be the notation or the operation separating the functions. You have your dx plus minus the integral of your f of 3x dx, and plus minus so on and so forth. By the way, I forgot to make some claim here. As long as your functions, both of them, in this case f and g, in this case the f subs, are all on the same interval. Okay, so all on the same interval, and if they are all integrable, that means it is true. Okay, so we're going to use this one here because some situations might involve multiple types of functions. We might see some polynomial function, a radical function, rational function, trigonometric function. So for it to be easier, you can break them into separate functions and use the separate rules. So you may use the power rule, you may use the constant multiple rule for each, or even the rest of the rules we're going to discuss later. So as mentioned, in the next video, we will have examples or illustrations for this specific rule. Thank you very much for watching. So what are you waiting for? Subscribe now.